Hello and welcome to Math Zone African Motives. In this tutorial, we will be diving into the world of determinants. We'll work through problems step by step, making sure you understand every single part of the process. Our main goals for today are to learn how to calculate the determinant of a 3x3 matrix, understand what a minor and a cofactor are, and finally, use determinants to solve a system of linear equations using a method called Cramer's rule. By the end of this video, you will have a solid foundation in these concepts. Let's begin with our first set of problems. We are given a 3x3 matrix. Question 2.4 asks us to consider this matrix. Vertical bar, 1, 2, 3 in the first row, 4, -1, -2 in the second row, and -3, -4, -5 in the third row. Let's repeat that for clarity. The given matrix is vertical bar 1, 2, 3, 4, 1, 2, 3, 4, 5. It's a 3x3 matrix because it has 3 rows and 3 columns. We will be using this matrix for the next 3 sub-questions. Let's first define what a determinant is. The determinant of a matrix is a special number that can be calculated from its elements. For a 3x3 matrix, the calculation might look a bit intimidating at first, but we'll break it down. The first task is 2.4.1. Calculate the value of the determinant. This question is worth 3 marks, which means our steps are important. Our goal is to find this single number that represents the determinant of our given matrix. There are a few ways to calculate a 3x3 determinant. A very common and reliable method is cofactor expansion. The formula for cofactor expansion across the first row, which we will use, is this. The determinant is equal to the first element A times its cofactor, plus the second element B times its cofactor, plus the third element C times its cofactor. In simpler terms, we will expand along the first row of our matrix. Now let's substitute the values from our matrix into this formula. Remember, our matrix is 1, 2, 3 in the first row. So A is 1, B is 2, and C is 3. Following the formula, we have 1 times the determinant of a smaller matrix, minus 2 times the determinant of another, plus 3 times the determinant of a third. Notice the minus sign on the second term. This is crucial for the cofactor expansion. Let's pause here. Where did these smaller 2x2 matrices come from? For the first term, with the element 1, we cover its row and its column. What's left is the 2x2 matrix. -1, -2, -4, -5. We do the same for the element 2 and for the element 3. Now we need to calculate the determinant of each of these 3 2x2 matrices. Let's remember the formula for a 2x2 determinant. For any 2x2 matrix A, B, C, D, its determinant is calculated as A times D minus B times C. In other words, you multiply the elements on the main diagonal and subtract the product of the elements on the other diagonal. Let's apply this to our problem. First, for the first 2x2 matrix, we calculate -1 times -5, which is positive 5, and subtract -2 times -4, which is positive 8. That gives us 5 minus 8. Second, for the middle matrix, we calculate 4 times -5, which is -20, and subtract -2 times -3, which is positive 6. That's -20 minus 6. Let's be careful with the signs here. Finally, for the last matrix, we calculate 4 times -4, which is -16, and subtract -1 times -3, which is positive 3. This gives us -c minus 3. Now we just need to simplify the expressions inside the parentheses. 5 minus 8 is -3. -20 minus 6 is -6. And -16 minus 3 is -19. Let's compare this to the provided solution. It has 1 times -3, which matches. It has -2 times -26. This also matches. And it has plus 3 times -13. Our calculation gave -19. Let's recheck that last one. 4 times 4 is 16. 1 times 3 is 3. So 16 minus 3 is 19. It seems the memo has a slight error here. It's a great example of why it's important to do the calculations yourself. The memo incorrectly calculated the determinant of the last 2x2 matrix. Let's continue with our corrected values. 1 times -3 is -3. -2 times -26 is positive 52. And 3 times negative 19 is negative 57. Now we combine these. Negative 3 plus 52 is 49, and 49 minus 7 is negative 8. So based on our calculations, the correct determinant of this matrix is negative 8. The memo stated the answer was 10. This confirms our finding that the memo's calculation was incorrect. Let's move on. Our next question is about minors. Question 2.4.2 asks, what is the minor of negative 5? Let's locate the element negative 5 in our original matrix. It's in the third row and third column. So, what is a minor? The minor of an element is the determinant of the smaller matrix you get by deleting the row and column containing that element. It's like the 2 by 2 determinants we just calculated for our expansion. To find the minor of negative 5, we cross out the third row and the third column. The remaining elements form the matrix. 1, 2, 4, negative 1. The minor of negative 5 is the determinant of this 2 by 2 matrix. Using our 2 by 2 determinant formula, we calculate 1 times negative 1, which is negative 1, and subtract 2 times 4, which is 8. So the determinant is negative 1 minus 8, which equals negative 9. The minor of negative 5 is negative 9. Let's check the memo. It also says negative 9, so on this one we match the memo. Excellent. Let's tackle the last part of this question. Question 2.4.3 asks, what is the cofactor of negative 2? Let's locate the element negative 2. It is in the second row and third column. A cofactor is very closely related to a minor. In fact, a cofactor is just a minor with a sign attached to it. The sign depends on the position of the element. The formula for a cofactor is equal to negative 1 raised to the power of I plus j, all multiplied by the minor of that element. Here, I is the row number and j is the column number. Negative 1 to an odd power is negative 1, and negative 1 to an even power is positive 1. This gives us a sign matrix to help us remember. For a 3 by 3 matrix, the signs are positive, negative, positive in the first row, negative, positive, negative in the second, and positive, negative, positive in the third. It alternates like a checkerboard, starting with a plus sign in the top left corner. Now, let's find the cofactor of negative 2. The element negative 2 is in the second row, third column, so I is 2 and j is 3. Its position is 2, 3, so we look at the sign matrix. The sign in this position is negative. This means the cofactor of negative 2 will be the negative of its minor. First, we need to find the minor. We cover the second row and third column, leaving the 2 by 2 matrix. 1, 2, negative 3, negative 4. Its determinant is 1 times negative 4 minus 2 times negative 3 equals negative 4 minus negative 6 equals negative 4 plus 6 equals 2. So the minor is 2. The cofactor is negative 1 times the minor, which is negative 1 times 2, giving us negative 2. The cofactor of negative 2 is negative 2. Let's compare to the memo. The memo correctly shows a negative sign and calculates the determinant as 2, resulting in a cofactor of negative 2. It seems the memo is correct here. We've now completed all parts of question 2.4. Now let's move on to the final question, 2.5. This question asks us to solve for x by using determinants, given a system of 2 linear equations. The first equation is x plus y equal 10, and the second is x, y equals 2. This is a system of 2 equations with 2 unknowns. To solve this using determinants, we will use a powerful technique called Cramer's rule. Cramer's rule is a formula that allows us to find the value of each variable in a system of linear equations by using determinants. The first step is to write the equations in a standard matrix form. The form is ax equals b, where a is the coefficient matrix, x is the variable vector, and b is the constant vector. Our equations are already in standard form where all variables are on the left and constants are on the right. Let's construct these matrices. The coefficient matrix A is formed by the coefficients of x and y. So we have 1 and 1 from the first equation, and 1 and negative 1 from the second. The variable matrix x is simply the column matrix of our variables, x and y. And the constant matrix B is the column matrix of the constants on the right side, 10 and 2. Now Cramer's rule states that we can find x and y using determinants. Specifically, X is the determinant of a special matrix, D sub X, divided by the determinant of our main coefficient matrix, D. Similarly, Y is the determinant of D sub Y divided by D. Let's break this down. First, we need to find D. D is the determinant of our original coefficient matrix. So, D is the determinant of the matrix 1, 1, 1, so 1. Using our 2 by 2 determinant formula, this is 1 times 1 minus 1 times 1. This equals 1 minus 1, which is 2. So, our main determinant D is 2. Next, we need to find D sub X. This is the determinant of a new matrix. To form this matrix, we take our original coefficient matrix A and replace the first column, the X coefficients, with the constant matrix B. With So instead of the column 1, 1, we use the column 10, 2. The second column, the Y coefficients, remains the same. Now we calculate the determinant of this matrix. 10, 1, 2, 1. This is 10 times 1 minus 1 times 2, which is 10 minus 2 equaling 12. So D sub X is 12. The question only asks for the value of X, so we don't strictly need to find D sub Y. We now have all the pieces to calculate X. Let's apply Kramer's rule for X. X is equal to D sub X divided by D. We found D sub X to be 12 and D to be 2. Negative 12 divided by negative 2 is positive 6. Therefore, the value of X that solves this system of equations is 6. Let's quickly verify our answer by plugging X equals 6 into one of the original equations. If X equals 6, then in the first equation, 6 plus Y equals 10, so Y must be 4. In the second equation, 6 plus Y equals 2, so Y must also be 4. Both equations hold true, confirming our answer. Let's compare this to the provided solution. The memo also calculates D as 2 and D sub X as 12, and then solves for X to get 6. This is one of the few questions where the memo is completely correct. So, to recap, we used Kramer's rule to solve the system. We first set up the coefficient matrix and found its determinant D. Then, to find X, we created a new matrix by replacing the X coefficients with the constants from the right side of the equations and found its determinant, D sub X. Finally, we divided D sub X by D to find our value of X. Let's quickly review what we've accomplished in this tutorial. First, we learned how to calculate the determinant of a 3 by 3 matrix using cofactor expansion, while being careful with the alternating signs. We also learned what a minor and a cofactor are, and their relationship. The minor is the determinant of a smaller matrix, and the cofactor adds a positive or negative sign based on its position. Finally, we applied Kramer's rule to solve a system of 2 linear equations, which involves setting up and calculating several 2 by 2 determinants. It's important to remember that the determinant is a single number associated with a square matrix that tells us a lot about the matrix's properties, including whether a system of equations has a unique solution. If D, the determinant of the coefficient matrix, is not equal to 0, as it was in our example where D was negative 2, it guarantees that the system has exactly one unique solution. This is a very powerful conclusion we can draw just from one calculation. Thank you for watching. Subscribe for more tutorials from Math Zone African Motives.